Okay, we're all going to get perfect attendance points today for the clickers. We won't use our clickers today. And we're going to talk about electric field lines. But first, I'd just like to review just a little bit where we've been. I hope that everyone's familiar with the two-step dance that we're doing here. Okay, the two-step dance. The first step in this two-step dance is that a source charge Q sub S, that's the Klingon, creates an electric field throughout the room, changes the room, okay? And we compute that at a particular location, the location of the X, with this formula that we call Coulomb's law. And we always use that formula just to find the magnitude of the electric field, how strong it is, always a positive number, okay? And then we use our gut to tell us what direction it points. If it's a positive source, a positive Klingon, the electric field's going to be away. If I was looking down here, it would be away. If I was looking up there, it would be away, always away, okay? And remember what the electric field is. It's got the waffle words. If I reach into my pocket, and if I pull out plus one coulomb, and if I put it at the X, how would it be pushed? Well, that positive source charge is going to push a positive 1 coulomb away. Like charges repel. If I had a negative Klingon, a negative source, the field would be towards. If I was looking down here, it would be towards. Up here, it would be towards. Everywhere, it would be towards. Now, that's the first step. The Klingon sets up the field, goes back to the home planet, okay? The second step is that that field exerts a force, an actual push. That's the sort of thing we talked about in Physics 105, okay? On a test charge, that's the Captain Kirk. And it happens through this formula, which we consider to be the operational definition of the electric field. And this here, it's a vector equation, and that's very important. And minus signs matter. They're very important over here. Over here, we got rid of all the minus signs by just looking for the magnitude. But here, the minus signs are everything. Because if the electric field is to the right, and my Captain Kirk, my test charge that's being pushed is positive, well, the force is going to be to the right. But if the electric field is to the right and my Captain Kirk is a negative charge, well, then it's going to be in the negative right direction, which we often call left. Check that your neighbor's okay with that. If you have a neighbor, some of you are kind of away from your neighbor today. Okay. So you saw this in your homework. 2-point charges plus Q and minus Q are fixed in place. And folks, that's important. Okay. The source charges, the Klingons, we're always going to fix in place. We're going to glue them to the sky. We're going to staple them to the wall. Because we don't want them flying away. That changes the problem, okay? All of these charges are putting forces on all the other charges, and we don't want them flying away. So we fix them in place, and they're a distance 2d apart. What direction is the electric field at the midpoint between the charges? Now, you came to believe in Physics 105 that student 1 is always wrong. And that's pretty accurate. Okay, so I put student 2 here. The electric field is given by this formula. So if I do the calculation, I put the plus Q in there and the minus Q in there, I get 0. So the electric field is 0 and has no direction. Wrong or sick and wrong?
Sick and wrong.
Sick and wrong, yeah. That's not the formula we use for electric field. We use the absolute value of Q sub S. And so we don't care about that minus sign. What we know is that the electric field at that X due to the positive Klingon is going to be to the right, away from the positive source. The electric field at that X due to the negative Klingon is going to be to the right, towards the negative source. Both of those contributions are to the right. They add, so it's not zero. Okay. We had this problem right at the end of class last day. We've got two positive charges that are identical, one at A and one at B. And we're looking for the electric field at point C. And we're told that this distance here between A and C is twice as far as the distance between B and C. So we use superposition. We first of all consider the positive source at B. It's going to give me an electric field away because it's positive. And then I consider the electric field due to A. Well, it's also positive, so I get something away, which would be down, but it's twice as far away. And the field depends on 1 over the r squared. And so that means twice as far away is 1/4 as strong. So I get a very little contribution from A. And when I add those two together, I get something that looks like C. Okay? And most of us got that right last day. Let's look at this from the tutorial. I hope everyone has figured out how we deal with extended charges, where we take the charge and we smear it like peanut butter along, in this case, a hemispherical rod, okay? And we're looking for the electric field right there at that X, okay? Now, our formula only works for point sources, sources that are small. And so we don't have a formula for a rod that's bent like that. We don't. So what we do is we break that up into chunks and we use superposition, okay? And so first of all, so each of these chunks, if I have 1, 2, 3, 4, 5, 6, 7, 8, 9 of them, each of those would have a charge of the total charge divided by 9. I could have made 1,001 points, but that would take us longer than we have. I did 9. Okay, if I look at the contribution due to this one here, it's going to be away. Because this is a positive charge, I get a contribution away. If I look at the contribution to the next one, it would be away. And then this one would be away, and this one would be away, and this one at the bottom would be straight up. This one would be away, this one would be away, this one would be away, and this one would be away. Now, let's say, I'm making this up, that each one of these contributions was 5. What units? Newtons for each coulomb. I made that up, 5. So I've got 9 of them. When I add those up, do I get 45? No or heck no? Heck no, thank you. Because I'm not adding them up, I'm adding them up as vectors. And when I add them up as vectors, these two completely cancel out. The field due to that one on the left and that one on the right, they cancel out and give me nothing. I'm just going to keep a scorecard over here, a ledger. Now, if I look at these two, that one there and that one there, this charge is giving me that field. This charge is giving me that field. But when I add them as vectors, they mostly cancel out. And I get a little contribution. Okay. Now I'm going to take this one here that gives me that field, and this one here that gives me that field. They cancel out a little bit, not as much as the earlier ones. And I add that. And then I do these guys, and I put it over there. And then finally, I've got the one at the bottom, and it's truly 5. That one's 5. And so I add it. And that gives me my total. But you were asked in the homework to compare the field due to this extended charge to a concentrated charge of the same size. And the way to think of that is to take your peanut butter knife and scrape all that peanut butter down to the bottom of that hemisphere. Okay, if I scrape all of that charge right down to here, I can think of all 9 of those chunks right here. And all 9 of those chunks now are giving me an electric field in the same direction. And it's 5, 5, 5, 5, 5, 5, 9 fives, okay? And so in that case, that's truly 45 newtons for each coulomb. And so if it's all together, it's going to give you a bigger contribution. The questions on that? That seem reasonable? Okay. Now, back in the day, back when I was alive, I had classes that were not this big. 570 students we've got now. And what I found when I hand graded the tutorial homework was that some of the students were drawing their pictures like this, and some of them were drawing it like that. See which way your neighbor draws it. Which way is your neighbor drawing it?
Do the top one. What that? Yeah.
Okay. Are they both fine? Is this tomato, tomato? You know, you do you, I'll do me. No. And by no, what I mean is heck no. Okay. Heck no. People that are drawing it like this are confusing charge with electric field. And I hear people use those words interchangeably. And that's going to just be a disaster on the next exam. I can promise you that's just going to lead to all sorts of problems. Charge is just too many electrons or too few electrons. Okay? It's not field. It's not field. Okay? The charge creates the field everywhere. But the field right here is not 5. The field over here is 5. Okay? If I look at that right there, when I put that formula, I got to put in an R. That R is the distance from the charge creating the field to where I'm looking at the field. Well, if I think the field's being created right there, the distance 0, divide by 0 squared, your calculator blows up. Okay, so this is just sick and wrong. We're looking for the field at the X due to these charges down here. Okay. What's the electric field in the middle of that circle? Shout it out. 0. Yeah. If I were to break this up into 1,001 little chunks of charge, for every charge that I've got over here pushing to the right, I've got a charge over here pushing to the left. Every charge up here pushing down, I would have a charge here giving me a field up. Okay, that all cancel out due to symmetry. Okay, you had a homework problem, and that's not the right number there. This would be 6.5. Actually 7.5. This was an old exam problem. And when it was on the exam, it caused a lot of grief. And you remember what we were told is that when a third charge of +4 nanocoulombs is placed at that X, 10 centimeters from QB, the electric force on QC is 0. Find the net electric field at the X. Well, people were high-centered for like half an hour, not knowing what to do. They said, well, Greg, I think there's a problem in your problem. I think you made a mistake because you didn't tell us what QB was. Well, if you tell us what QB is, we could tell you what the electric field at the X is. You do your part, Greg. Okay. And what they were missing was this operational definition of the electric field. You are told that the force, this is zero. You were told the QC is not zero. What does that tell you about E? Yeah, if that's zero, that's got to be zero. It's that easy, you know, and getting hung up for a half hour just because of a zero, that's tragic. Don't let that be you. Turn to your neighbor and say, that'll be you, not me. Okay. Okay. The next thing we were asked to do is to find the electric field at the X due to QA alone. And we want the magnitude and the direction. Well, the direction is pretty easy. QA is a positive source, a positive Klingon. And the field due to that is going to be away. And so I'm going to get something to the right. And if I plug into our Coulomb's law, KQA divided by R squared, I get a number that's 600 newtons for each Coulomb. You got a different number because you got a different distance right here. Everyone did. But if we use 20 centimeters here, we get 600 newtons for each Coulomb. Well, part C asked us to find the size of QC, of QB rather, this one here. And we want to know how big it is, magnitude, and we want to know whether it's positive or negative. Well, the sign is pretty easy, okay? I got to make the total electric field of that X zero. If the contribution due to A is 600 to the right, the contribution due to B had better be 600 to the left so that it adds up to zero. And that tells me immediately the QB has to be a negative source charge, a negative Klingon, does it not? Now there's two ways to find the size of QB. One way is just to plug into the formula. E is equal to, so in this case, E is equal to QB divided by R squared and multiplied by K. So I'd say 600 is equal to K times QB divided by 10 centimeters squared. And I could get a number with my calculator. But I think there's a much better way. And that's just to use proportional reasoning, okay? The answer turns out to be this value here, which is exactly 1/9 of that value there. Well, why does that make sense? Well, suppose that both of these charges had the same size, that they were both 6 nanocoulombs. Well, this charge is 3 times further away from the X than charge B, right? This one's 30 centimeters away. This one's only 10 centimeters away. If the charges were the same size, this one would give me a contribution that was 9 times bigger. 3 times closer is going to be 9 times bigger because of the 1 over R squared. I don't want a field that's 9 times bigger. I want a field that's the same size. So that means my charge had better be 9 times smaller. So if I take this charge and I divide it by 9, I get that number there. Check on your neighbor again. Do a buddy check.
That's just a shortcut way of it. I think you know.
I agree. Yeah.
Probably what I'll do.
Okay.
But I get like the.
Who's this? Come on, somebody's got to know. Nobody knows?
Pepe LePew.
Pepe LePew. Pepe LePew. How many of you have watched a Pepe LePew cartoon? Yeah, that's just a crying shame. Okay. Pepe LePew was a very popular cartoon back when I was alive. Okay. And there were lots of different episodes, but only ever one plot. And that plot was that Pepe's lovesick, and some cat wanders into his neighborhood and accidentally gets paint, a stripe of paint down her back so that she looks like a skunk. And then the chase was on. And so what we get, let me. Gentlemen, that's disgusting. No means no, okay? This cartoon ruined a whole generation. Pepe LePew is a criminal, okay? It's a criminal. So why do I have Pepe LePew in the lecture? Well, in the cartoon, the people that were doing the animation had a very unique problem. And that is Pepe stunk. He was stinky. And yet you couldn't convey that stink very well to a TV because you can't transmit stink through a TV. You can't say, "Oh man, that stinks like Pepe." Okay? And so they had to figure out a way to help people imagine or visualize where it was stinky. And the way they did that was with lines of stink. Okay? And so you would see this wall and these lines of stink coming out from behind them, and you would say, "Oh, Pepe's behind that wall. I know Pepe's behind that wall." And the closer those lines got together, the stinkier it got, okay? Until you knew when they were really close together, Pepe, okay? Now, just like stink is invisible in a TV, this electric field that we're talking about is invisible. It's a vector field, okay? Every point in this room has a vector associated with it that has both length and direction. When we were talking about the gravitational field, yeah, every point in the room had a vector associated with it, but it was always the same vector, 9.8 newtons per each kilogram down. And so rather than have the whole room have an infinite number of vectors, we just said, just give me one. That'll do. I'll just use it everywhere in the room. But if this PC is positive and this iPad is negative and this calculator is negative, the electric field in this room is going to be drastically different from point to point. Some places it's going to be strong, some places it's going to be weak, some places it's going to point this way, and some places it's going to point that way. And if we were to fill this room with all the vectors, what does it look like here? 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 This room would be filled with vectors going every which direction, and it would drive us mad, okay? And so we need some way to paint a picture that will let us visualize what the electric field looks like everywhere in the room, and then we'll use that to find the electric field at a particular point, okay? Now, we're going to use the same idea that Pepe LePew's terrible creators came up with. Now, the closer we get to the source, the closer together the lines of stink. And what if I got a really hot day where he's really stinky? If it's a hot day, I just have more lines of stink. So the greater the stink, the more lines I use to represent it. Now, if I just have one charge and it's a point charge, it's symmetric, it's spherically symmetric, the electric field is going to be radially outward, okay? And so this is kind of a representation there. I need someone with really fine blonde hair, but not too long. That's not quite blonde. Yes, that'll do fine. Come on down. Yes, yes. You were made for this. Yes, you were. Okay. Hop apart on this stand here to keep you from getting fried. Put your hand on that Van de Graaff generator and don't let go, okay? Just don't let go until I tell you it's safe, okay? Now, okay, shake your head a little bit. Ah, you're getting there. You're feeling it? Oh, you got the arm hairs sticking out?
Oh, yeah.
Okay. Your leg hairs? Oh, there it is on your head. Shake again. Okay. That's pretty darn good. Okay, don't let go. I'm gonna, don't let go. Ooh, that got me. Did that you too? Yeah. Okay, let's give him a hand, folks. So in Bozeman, rather than this platform here with the ceramics, we just had this great big wooden block. And, you know, the first time I used it, I had this student up there and she was complaining, ow, ow, ow. I said, oh, you're fine. You're fine. Stop complaining. What was happening was we made the wooden block uh, out of pieces that were hammered together with metal nails, and she was arcing down to the ground, and she was getting zapped over and over again. So we had to get a different block. So we can try it with this guy. There we go, Garfield. Let's see how he does. Okay, there we go, Garfield. Now, if our Van de Graaff was strong enough, those would be radially outward by symmetry, radially outward. They're getting there. Okay. Now, there we go. We can also have some fun with this. If I put that up there, put a bunch of little pie pans there. We can make a mess. Okay, that's enough fun there. So if my source that's creating the field is symmetric, then my field lines should be radial, away or towards, depending on whether the charge is positive or negative. But more importantly, and this is critical, they have to be evenly spaced, okay? If I go out in, say, 2 centimeters in any direction, I expect the field to be the same strength. I expect it to be the same strength here at 2 centimeters as it is over here at 2 centimeters. And we represent the strength of the electric field, just like with lines of stink, by how close they are together, next to each other, okay? How tightly packed they are. And so this would be a strong field close and a weaker field further away where the lines are further apart. Now, I just want to point out that this picture comes from my competitor, Paul Hewitt, that has 98.5% of the market share. And it's wrong. It's sick and wrong, okay? And the reason it's sick and wrong is because when we put the arrowhead at the end of the line, that's a vector. And a vector only has one direction. It gives me the direction of that quantity at one location. But field lines can bend. We're going to find that they can be all sorts of different shapes, okay? And so we differentiate between field lines and vectors by putting the arrowhead in the middle of the line. And so these are just sick and wrong, sick and wrong. Now, I have a friend, we used to share an office together, and he went off to Microsoft and became very, very wealthy, retired at the age of, I think he was 38. So anyway, while he was still working in physics, he created a program that is called EM Field. And it turns out that this program was meant to run on an 8-bit processor. And it's never been rewritten for modern computers. And so what I had to do is actually create a virtual machine that's running Windows XP. We're going back to the before times, okay? And so you'll be patient with me, please. This program allows us to put charges in this space. I'm going to take a -4 and put it right here. And I'm going to take a +5 and I'm going to put it right there. Okay? Now, that could be -4 coulombs and +5 coulombs, or that could be -4 nanocoulombs, and this could be +5 nanocoulombs. It's just a 4-to-5 ratio, and one's negative and one's positive. Now, he allows us to choose what we want to plot, and I've chosen vectors. And so if I click on any point, it's going to give me a vector that represents the field, not just due to the -4 and not just to -5 or the +5, but the electric field due to both, okay? Now you'll notice that when I'm really close to the +5, it dominates and I get really, really big electric fields. And when I'm close to the -4, it dominates, okay? But when I get out here, I get something that's smaller. Now, like I said earlier, I could click on every single point in this space, and I would have an infinite number of vectors, and that's just a mess. That's just a mess. So what I'm going to do is I'm going to, and I can do this. I can move it around, and you can see how it changes with location. Big. Big. Okay. Let me clean that up. Now, he also wrote the program so that we could have directional arrows. these directional arrows tell me the direction of the electric field, but not the magnitude. All the arrows are the same length. And so if I click anywhere, I just get arrows that are the right direction, but they don't tell me about the magnitude. Now I'm going to do something. I'm going to start right here at this +5. I'm going to click and create a directional arrow. And then I'm going to march out to the end of that arrow, and I'm going to click again. And then I'm going to march to the end of that arrow and click again, and then to the end of that arrow and click again. Anyone want to guess where this is going to end up? Whoa, this looks suspicious. Okay. It ends up at the -4. Now, we call that a line of force, and that will be the topic of this week's tutorial. And we call it a line of force because everywhere along that line, the electric field is going to be tangent to that line. That's what those little arrows mean. So if I went back to the field vectors and I clicked anywhere along that line, I get a vector that's tangent to that line, okay? And the closer I am to the charge, the bigger that vector is, okay? Now, the program will do the stepping for me. Instead of me stepping every, centimeter or so, the computer will go and just take an infinitesimal step and then recalculate the direction and take another step and take 1,000 different steps to get from one place to another. And David Trowbridge essentially did the stepping for us, and we call those field lines. And so you see that if I just click right here, I get a field line. Now, I'm going to make 5 field lines that are, I tried to make them evenly spaced around this +5, because I know that near the +5, I got to have symmetry. The field has to be the same strength no matter whether I go northeast or whether I go southwest, okay? Now, if I use 5 field lines to represent my +5, I need 4 field lines for the -4, so I'm missing 2 field lines, okay? And those would be a set of field lines, but not a very good set. I'm going to get more information by coming in and putting another field line in between every 2. I'm going to try to make these evenly spaced, but I'm fairly human, my wife says. Okay, so now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 field lines representing the +5. So I should have 8 for this guy. I've got 1, 2, 3, 4, 5, 6, 7. I'm missing 1. Okay, so those are my electric field lines. I just painted a picture of the electric field everywhere in that region. And I can go in and see if it works. If I go back to the vectors, where the field lines are close together, I get a big vector. Where the field lines are far apart, I get a small vector. And anywhere close to one of these lines, the vector is going to be tangent to the line. And if I'm looking somewhere between the lines, I have to take the direction tangent to this line and tangent to that line and kind of average out. It's kind of the average of the two. Okay, and so if I look over here, my electric field vector is going to be tangent to the line. Here it's going to be tangent to the line, and where they're close together, it's going to be big, and where they're far apart, it's going to be small. See if your neighbor understands what's going on here. What are these field lines telling us about the electric field? Is it painting the picture for you?
Yes.
I want you to know that we spared no expense. We spent your tuition money on these.
I get the one. It's just, yeah, I get that.
Questions?
The lines are.
Okay.
Yeah, I got one.
Yes.
Does this even tell us, Professor?
What's that?
What the heck does this even tell us?
What does what?
What does this even tell us?
Oh, it tells us where the electric field is strong, where it's weak, what direction it points at any location. Okay, and so I can give you a set of field lines and ask you, is the electric field stronger at point A or at B? Okay, is it stronger at point A or at point B? And it also tells me, if I did not tell you, if I did not label that as a +5, and if I did not label that as a -4, first of all, David Trowbridge's program didn't put the arrowheads. But if I gave you field lines, I would have an arrowhead pointing along this line away from the plus towards a minus. So the arrowhead would be to your left here, to your left. And so by looking at that arrowhead, you would know that this is a positive charge and this is a negative charge. By counting the number of field lines, you would know that the size of the charge is a 5-to-4 ratio. That I've got 10 field lines around this one and only 8 around the other one. Okay, so it's a way of just being able to see the relative strength of the field and the direction. Now, if I go back, this is a summary. The direction of the electric field vector, that's a straight line with an arrowhead at the end. That vector only gives you one value for the electric field. How big the electric field is at the tail of the vector, okay? That vector is going to be tangent to the field line that it's next to. The magnitude of that E field vector, the length of the vector, is going to be proportional to how close the field lines are to each other. When they're really tightly packed, you have a very strong, stinky field. And the number of lines leaving or entering a charge is proportional to the size of the charge. Twice as much charge is going to have twice as many lines. And these lines leave positive charge and enter negative charge. Leave positive charge and enter negative charge. Now, let's practice that, okay, with Pepe. What direction would the force point on a small positive charge at points 1, 2, and 3? Okay. So if I look at point 1, well, I just use the fields and I say, well, it's tangent to that field line in the general direction of the arrowheads on the field lines. If I look at 2, tangent's going to be like that. If I look at 3, well, it's not on a field line, so I've got to kind of interpolate is what we call it when I take the average between the two, and it's going to be something like that. Now, if I have this small positive charge, how would I compare the size of the force on that charge at 1 and 2? Well, this is what really, really is tragic. Again, I'm an old man, and I've seen this over and over again. On exams, what students tend to do is they say, oh, well, I got a lot of field lines coming from that, coming out of it. That's a big positive charge. I got a lot of field lines going into that. That's a big negative charge. And then they start using Coulomb's law to figure out how big that field is. And then they do the same thing over here, and they say, well, that's not so big, but it's positive. And they waste a lot of time because they've thrown away the gift. I went to a lot of trouble to make those field lines with the computer, okay? I did my part. What you need to do is accept the gift and be grateful for it and say, hey, the field lines are close together there. That's a big field. The field lines are far apart there. That's a little field. Bada boom, bada bing. Bada bing, bada boom. Whatever it is, you know. Okay? Now, if I compare 2 and 3, well, they're closer together at 3 than they are at 2. So it's going to be bigger at 3 than at 2. Now, what if I double the test charge when it's at 2? Well, the force is going to double as well, because you remember that operational definition of the electric field. The electric field doesn't care about how big the test charge is. The test charge doesn't create the electric field. The electric field is created by A, B, and C. Okay? And so the electric field stays the same whether I use a little test charge or a big test charge. But if I look at that formula, the force is equal to the size of the test charge times the electric field. If I double the size of the test charge, I double the force. But the field stays the same. But the field stays the same. Now, questions on that? Yes, sir. Just a second.
I'm just wondering, wouldn't the test charge also have its own electric field?
Yes, it does. It does. But the field that's pushing on the test charge, and we will explore this in this week's tutorial, is not its own field. Okay? The test charge doesn't push on himself. Okay, it's the field due to the other charges that is going to be pushing on the test charge. And we're going to explore that in great detail in this week's tutorial. Thank you for asking that question. Here's a problem that is in your homework. You have a large metal ball that's neutral. I know it's neutral because I touched it. Okay? And then I bring up a negative point charge right here, and I'm asked some questions about this location over here, the X. What's at the X? Nothing. Empty space. The X is just a location, an address. Okay? I'm first asked to find the direction of the E field at the X due to this negative point charge alone. Forget about the metal ball. Forget about the metal ball. Well, I know that since it's a negative source, my electric field had better be towards that negative source, right? That's what we decided, always towards a negative. And then we're asked, well, what is that negative source? What does that do to the electrons in my metal ball? In a metal ball, the electrons are free to flow to their happy place, to go where they're comfortable. how are we gonna, how are they gonna move if I've got this negative charge over there? Which way are they gonna flow? Yeah, they're gonna want to flow away from that negative source. They're gonna want to get over here, okay? Well, now I've got three Klingons creating field at the X. I've got this one that I've already covered. I've got these positive charges and I've got these negative charges. So when I add those three together, am I going to get a total electric field that's bigger than that purple one that I started with, or smaller than I started with, or the same? So we're not going to use clickers because we're all getting a perfect score today, but decide how you would vote if you were going to use your clicker, and then tell your neighbor real quick. How would you vote?
The deceleration, people reaching the positives. So will it cancel each other out, or does it just get slinged?
Okay. Is the total field going to be greater than that purple one, less than, or equal to? Those who say greater than, those who say less than, those who say equal to. Okay. Again, we've got three Klingons. We've got the contribution due to this one that we've already shown. And then I have a contribution due to these electrons that are over here. And I put that in dark blue. And then I have a contribution to these naked protons over here, and I put that in dark green. Now, why did I put the green arrow shorter than the blue arrow?
Farther away.
Because they're further away, and distance matters a great deal. Okay, and so now when I add these three up, I get a total that's bigger than what I started with just the point source alone. So that neutral metal ball actually magnified the electric force on the other side of it. Okay, which is a little counterintuitive, I think. A little counterintuitive. Now, the answer is A. Now, just in summary, this is the last slide, and I'll let you go listen to a prophet's voice. At any point, if I've got those field lines, I can just put a vector that is in the general direction of the field lines. And if the field lines are close together, I put a long vector to represent, this represents the electric field at that point, at the tail of the vector, at the X. If I do it for this one here, it's shorter because they're further apart. And this one's right on the line. Is that important? No or heck no? No, it's how close the lines are together. And so I get a short vector there. The fact that it's on a line makes it easy for me to find the tangent direction, but that's it. That's it. Okay, folks, let's go to devotional and listen to the prophet. Thank you for coming early today. I love you guys.
Yep, I've seen this.
About this. About this.
Let me stop this.